Okay. All right. So, last time I begun by defining linear transformations. So, here was the definition. So, you have some transformation that is really just a different name for a function. So, but specifically, we're interested in transformations between Rn and Rm. So, um, to n and m dimensional. We'll talk about dimension later in the course, but to n and m dimensional real vector spaces. We'll talk about vector spaces later, and you'll see where all this stuff is kind of wrapped up. So anyway, this is specifically a function between n and m dimensional Euclidean space. So what this looks like is it takes in vector in Rn, spits out vector in Rm. So the collection of all the vectors you're allowed to take in is the domain. For us, we're not going to worry about restricting this at the moment. So it's in this case, its domain would be all of Rn. Its range, however, is some subset of the codomain Rm. So I will talk about examples of, for instance, transformations that don't have a range that is all of the codomain. For example, here's one easy case. Imagine a transformation I define that takes everything to the zero vector, right? Whatever vector it spits in, or you put in, it spits out the zero vector. Is that a transformation? Absolutely. Is that a linear transformation? In fact, it is a linear transformation, even. And it's an example of a linear transformation whose range is just the zero vector. So its range is a single point sitting inside the codomain. All right. So anyway, so that is just a transformation. Literally, the only requirement for a thing to be a transformation in this sense is that it be a function, right? In the classic sense, right? So you put in one input, you get one output. You don't get multiple outputs for a single input. Okay. So to be linear, it must satisfy these two things. That is, it splits up across sums, and you can factor scalars out of it. Right, that's the easy way of remembering what this thing does. So it is linear if t applied to a vector sum is a sum of those transformations. So t of u plus t of v, and t applied to a scalar multiplication of scalar times vector is actually scalar times t applied to the vector, right? So I can pull scalars out of linear transformation, and linear transformations break up across sums, right? They split up across sums. And this has to be true for every single vector in the domain. All right, which I tidied up as saying it's linear if it respects linear combinations. Okay. Now, at the very end of class, I said, well, what are examples of linear transformations? So our first example of linear transformations are going to be matrix transformations. So I give you a matrix. This is going to define a linear transformation. And the reason why it's going to be linear is because of those facts about multiplying matrices by vectors that we talked about a few lectures ago. Of course, there are some linear transformations that are not technically matrix transformations. Those are examples like integrals and derivatives are examples of these things. Now, it turns out that with one tiny assumption, essentially every linear transformation is a matrix transformation. And so these are by far going to be the most important thing that we talk about. So let's see an example of those. So here's an example of a matrix transformation. So let A be the following matrix. I'm going to read row-wise here. So 1 minus 3, 3, 5, and minus 1, 7. Okay, so that's A. Let U be the vector 2 minus 1. Let B be the vector 3, 2, minus 5. And let C be the vector 3, 2, 5. Okay, so define a transformation T, okay, that is going to go, I'm going to leave these open for now. So I haven't put these, don't think that I'm saying this is a transformation from the reals to the reals. I haven't filled these in yet Okay, so I haven't filled those in. So it goes from somewhere to somewhere, and I've defined it by t of vector x is a times x. Now let's think for a second. In order for this to be defined, how did I define multiplying a matrix by a vector? So in order to multiply a matrix by a vector, so the vector itself had entries. Those entries were the weights, and I just formed the linear combination of the column vectors times those weights. Well, here I only have two columns. So if I want a times x to be defined, what does this exponent need to be? It's got to be 2. Okay, and since so I get a linear combination of two vectors that have 3 entries. So this goes from R2 to R3. Okay. So since I'm defining this as matrix product AX, then this is my only option here. So my transformation goes from R2 to R3. That is, it takes in a vector X in R2 and spits out a vector in R3. So then I want to write this as my matrix A. So 1, minus 3, 3, 5, and minus 1, 7, times a generic vector x. So a generic vector x in R2 is just x sub 1, x sub 2 here. Well, how do I do this multiplication? So I form linear combination, x sub 1 times first column, x sub 2 times second column. So this is x sub 1 minus 3, x sub 2 in the first entry. In the second entry, this would be 3 x sub 1 minus 5, or sorry, plus 5 x sub 2. And in the last column, this would be minus x sub 1 plus 7 x sub 2. Right? Okay, there's my transformation. And so if I want to know how this thing acts on a vector that has entries x sub 1 and x sub 2, I put in this vector, x sub 1, x sub 2, and it spits out a vector in R3 that has these 3 entries, okay, defined in this way. All right. There's no x sub 3 here because it wouldn't make sense then. Remember, you can only, when you have a matrix and it has n columns, then to multiply it by a vector, that vector has to have n entries. So since A has 2 columns, it only makes sense if this vector has 2 entries. Okay, otherwise that product's not defined. So we'll talk about that when we talk about multiplying matrices in general. So matrix products are not always defined. So the only way this could be defined is if I have a vector with 2 entries there. Okay, so here's what my transformation looks like. Okay, now a couple questions. So one, find t of u. What does t of u look like? Right. So I can either use this formula that I've gotten for t, or I can just do this directly. So t of u then is going to be a times the vector u, which is matrix 1 minus 3, 3, 5, minus 1, 7, times the vector u, which is slightly off screen now. It's 2 minus 1. Okay. So multiplying this out, what do I get? I get 1 times 2 plus minus 3 times minus 1, so that is 2 plus 3, so that's 5. Again, you could have used this formula, right? So in the next slot, I would get 3 times 2 plus 5 times minus 1, so that's 6 plus minus 5, so that's 1. And then lastly, I would get minus 2 plus 7 times minus 1. So that's minus 2 minus 7, so that's minus 9. Okay. All right, and so one way of saying this is that the image of u under this transformation t is the vector 5, 1, minus 9. Okay. All right, so here's another question. In fact, maybe I'll ask this on the next page just so I have more room. So second question, find an x in R2 whose image under t is b. Okay. So how do I do that? i.e., I want to solve the equation t of x is equal to b. But how is tx defined? Well, on my sheet of paper here, t of x is a times x. So, i.e., I want to solve ax equals b. Aha! Right? So now it is clear how recasting this equation as some other type of question goes. So really, I started out with a question about finding a vector whose image under a transformation t is b, but since this transformation is a matrix transformation, this was actually the same as asking to solve the equation ax equals b. So note, imagine you had never heard of a transformation in your life, and I asked you to find an x whose image under some transformation is b. You're like, I don't know what a transformation is. But once I tell you, oh, actually, it's just solving this matrix equation, then if you know how to solve the matrix equation, you could answer that question anyway, right? So again and again and again, we're seeing that every single one of these, every single time we come up with some new concept, we can immediately tie it back to this matrix equation, ax equals b. And so you know that what I said on the first day of class wasn't lying to you, that basically this entire class is studying the equation ax equals b. Right? Okay, so I want to do this. But how do I do that, right? So I want to solve ax equals b. But solving ax equals b means doing what? Well, that system, I'm just going to write this again. So this is 1 minus 3, 3, 5, minus 1, 7 times a generic vector x sub 1, x sub 2, and that's equal to the vector b. So just to remind you, b here we said is 3, 2 minus 5. All right. Okay. So what does it mean to solve this system? Well, I write up the augmented matrix and I row reduce it. Right. That's something you've certainly never heard before, right? So writing up the augmented matrix here, this is 1 minus 3, 3, 3, 5, 2, minus 1, 7, minus 5. I want to row reduce this thing. We already have a nice pivot position in the upper left, so I'm going to row reduce it by zeroing out these two entries below. So I have 1, 3, minus 3. Zeroing out these two entries, I'm just going to go ahead and copy this. This is 0, 14, minus 7. That's multiplying these by minus 3 and adding, replacing row 2. Doing the same thing, replacing row 3, I get 4 and, minus 2 here. Okay. All right. So now dividing by 14 in the second, and then using that to zero out what's below it, I get there's a minus 3 here. I reversed these. That's fine. So this is 1 minus 3, 3, 0, 1, 1 half. That's minus 1 half, I guess. And then this actually zeroes out the bottom row entirely. I can keep going till this is in reduced row echelon form. So this is 1, 0, 3 halves, 0, 1, minus 1 half, and 0, 0, 0. Okay. Thus, x sub 1 is 3 halves. X sub 2 is minus 1 half. All right. So x is the vector 3 halves minus 1 half. All right. And you can check, if you want to, that t of x is equal to b. Right. Okay. All right. So that's how that goes. Okay. Now, here's a third question I could ask. Is there more than 1x such that t of x is equal to b. So in part, in our second question, we found that if we wanted to solve the equation t of x is equal to b, that's solving ax equals b. We found that solution here. Well, in solving this, what did we find? We only had two variables we were solving for, and we just found a solution, right? There was no free variable. So what does that mean about this question? Is there more than one x that satisfies ax equals b here? The answer is no, right? No. We already found the unique vector. We already found the unique solution. Right, so there it is. This is the unique solution, and there's not another one because there's no free variable here. Okay, if we had found a free variable so that we had just picked one, then the answer to this, of course, would be yes. All right. I need a little bit more room for the last question I want to ask. So last question I want to ask. Determine if C is in the range of T. Okay, now let me go back to all these things I defined here. So my transformation T is defined as taking my matrix A and multiplying it by my vector in R2. Asking whether or not C is in the range of T is the same as asking what? So here's my C, here's 3, 2, 5. Asking whether or not this is in the range, what is that asking? So i.e., does there exist an x such that t of x is equal to c? That's what I'm really asking. Okay. Yeah, so someone said, is it in the span? So that is definitely what it's related to. We will discuss all those things. There's about 5 gazillion ways you could rephrase this exact same question. Okay, but what does it mean for C to be in the range of T? What it means for a vector to be in the range of a transformation is it means there exists an x in the domain. So there exists an x in R2 such that T of x is equal to C. But since T is a matrix transformation with matrix A, i.e., does there exist an x such that AX is equal to, not C, or not B, equal to C, is another way of saying this. But if all I care about is whether or not this is in the range, that is, that there exists an x such that T of x is equal to C, i.e. that there exists an x such that A times x is equal to C, I'm viewing this as a binary thing, right? I'm actually just interested in yes or no here. So I don't actually care what this x is, I just care that it exists. So really another way of saying this is so i.e. is the equation AX equals C consistent? I just care that there exists at least one. That's all I care about. Okay, so note, these are 4 equivalent questions that I could ask you. Now, why is it important that I'm going through all of this in this way? Because on an exam, I could ask you any one of these things. So let's say that I want you to say whether or not AX equals C is consistent. If I wanted to switch it up, I could ask you any of these things and I'd be asking you the same question, right? So this is how these things are going to go. When I give you an exam, I'm basically going to run through the entire list of possible ways I could ask you something. So even if every single question is having you solve AX equals B, it won't seem that way because I'm going to be asking it in literally every possible way I can ask it. Okay. All right, so this is what I'm really wanting to know here, right? Okay, so is AX equals C consistent? Well, to answer that, what do I do? So let's remember our parameters here. So here's A, here's C. So I need to form the augmented matrix where C is my last column here. So form augmented matrix. So form AC as my augmented matrix. What does that look like? So reading row wise as usual, this is 1, minus 3, 3, 3, 5, 2, and minus 1, 7, 5. Okay, so now row reducing this a bunch. So row reducing this, I get 1 minus 3, 3, 0, 1, 2, 0, 14, minus 7. And row reducing it one more time, what do I get here? I get 1 minus 3, 3, 0, 1, 2, 0, 0, minus 35. Okay, note the last row corresponds to the equation 0 is equal to minus 35. Right? We're in that case, we're in the augmented matrix, we have 0, 0, 0, blah, 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 and then in the very last entry, something that's non-zero, and we know that that's bad. Okay, so we know that this is bad, i.e. AX equals C is inconsistent, which of course means that C is not in the range of T. Now, why is this important in general? Notice this T that I defined here is just this matrix equation, or it's defined by this matrix A. So this is what my transformation looks like. But note that, like, if when you first saw this and you said, okay, R2 is the domain, and I called R3 the codomain, right? And I made a distinct point to mention the codomain is not the same thing as the range. The range of T sits inside R3. It sits inside the codomain, but it's not necessarily equal to it. In some of these transformations, it will be equal to the entire codomain, but that's a special thing. We call that an onto transformation or a surjective transformation. Okay, but not always. In fact, here's an example. This T does not contain C, right? Our C is the vector 3, 2, 5. Nothing special about that vector. That vector is definitely an inhabitant of R3, right? It lives in R3, but it's not in the range of T. So the range of T is not all of R3, right? Is another way of saying this. Well, this is a more specific thing, but i.e. the range of T is not all of R3. So the codomain is R3, but the range of T is not all of R3. Now, just looking at it, maybe you're like, how would I even tell that's the case? So there are ways of thinking about this, but anyway, we'll discuss those a little bit later. So we had this definition of what a linear transformation is. Where did I put it? I have it written. Oh, here we go. So here's my definition of a linear transformation, right? So was that transformation I just defined linear? Yes, because it's a matrix transformation, and matrix transformations are linear like that. It can be written as AX equals B. Okay, now, what if I give you a transformation and I don't give you a matrix associated with it? I just tell you what the transformation does, and then I ask you, is the transformation linear? Okay, well, how would you check? So technically, to check, you have to really prove that it satisfies those two properties that I just took off the screen. But there are some quick ways that you could check things. So fact, right? I'll break it up as two facts. So if T is a linear transformation, then T of Cu plus dV is equal to Ct of U plus dt of V, right? For all scalars C and D, and for all vectors U and V that live in its domain, right? I didn't specify. Oh, I'm slightly off the page. So this is just saying that I can do both of those things simultaneously, right? This is combining both of these things simultaneously. And that's what I meant by it's linear if it respects linear combinations, because here's a generic linear combination that this transformation is respecting. So if it's a linear transformation, it satisfies these. But also, note that if T is a linear transformation, then, because of this fact, what is T of the zero vector? Well, I could say T of the zero vector is the same thing as T of the vector U minus the vector U, right? Because any vector minus itself is the zero vector. So T of U minus U is the same thing as T of the zero vector. But by this fact here, this is T of U plus minus 1 times T of U, right? i.e., this is T of U minus T of U. But what's T of U minus T of U? This is the zero vector. Okay. So this is the zero vector. So if T is a linear transformation, then I just proved that T of the zero vector is equal to the zero vector. Now, this is a slight abuse of notation. The reason it's a slight abuse of notation is that these zero vectors could be different sizes. So remember, my transformation T could go from R, say 5 to R17. So its input zero vector would be the zero vector that has 5 zeros as entries, and its output would be the zero vector that has 17 zeros as entries. But the point is that I don't care. It's the zero vector in whatever space it's living. Okay. So that's the point. So these are two ways of doing it. So if I give you a transformation and it doesn't satisfy this, if it doesn't satisfy that T of 0 is 0, then it's not linear. But the converse of this is not true. Okay, so converse is not true. Okay, what that means, the converse statement, right? If you have a statement, if P then Q, the converse statement is if Q then P. There's no logical relationship in general between the truth of a statement and the truth of its converse. If both a statement and its converse are both, share the same truth value, that's an if and only if statement. That's what an if and only if statement is. Okay, is it's a combination of two statements, statement and its converse. But the converse of this is not true. So if a transformation sends the zero vector to the zero vector, that doesn't mean that it's linear. So there's some pretty easy examples you can cook up that I'll have you cook some of those up, maybe for your next homework. And this is just a quick way of checking, but it's not it doesn't prove that the thing is linear. So anyway, what's important here? So as I mentioned, under some mild assumptions, every linear transformation is a matrix transformation. So there are some assumptions, so you can't say this absolutely, but under some mild assumptions, namely that you're dealing with finite dimensional spaces, every linear transformation is a matrix transformation. Okay. So what does this allow us to do? It means, so what this means is that associated to every linear transformation, that is under these assumptions that we're going to be under for the rest of the course unless I specifically say otherwise. So what that means is that associated to every linear transformation, there is a matrix. Okay. So this is codified in the following theorem. So let T be a linear transformation from Rn to Rm. Okay, then there exists a unique matrix A such that T of x is equal to Ax, okay, for all x in Rn. Okay. So in fact, A is the m by n matrix whose jth column is the vector T of E sub j, where E sub j is the jth column of the identity matrix in Rn. And so what is this A? This A is the matrix T of E sub 1 as its first column, T of E sub 2 as its second column, and so on up into T of E sub n as its nth column. Okay. Okay. Okay, so a couple of things here. I haven't actually defined the identity matrix yet. So this is, these E sub i's or E sub j's are also called the basis vectors, the standard basis vectors. But we'll get more into that in chapter 4 stuff. We'll talk about why they're called that. You know, these are, so E sub 1, 2, and 3 are the ijk vectors, right, from Calc 3. What's the n by n identity matrix before I go on? So here is the identity matrix in R3. So here's the 3 by 3 identity matrix, which we write as I 3 by 3. So the 4 by 4 identity matrix is this thing. So this is the 4 by 4 identity, or the identity matrix in R4. So then its columns are E sub 1, E sub 2, E sub 3, E sub 4, and these are in each case, right? These would be in R4 for this matrix, but they would be in R3 for this one. All right, so that's why we're not going to use different notation here. This is context specific, so that we don't have to have like a million subscripts and superscripts for everything. Okay, so this is what is meant by those E vectors. And so what this is saying, going back to this theorem, is that we can find the matrix associated to any so we can find the matrix associated with any linear transformation by taking my transformation defined in whatever way, right? So maybe my transformation is given to me in words, right? So I say T is the transformation that takes a vector in R2 and rotates it 90 degrees counterclockwise. Okay, so I'll say that's my matrix T. So T is the matrix, it's the transformation that takes vector and rotates it 90 degrees counterclockwise about the origin. All right, so what this is saying is that I have a very nice way of actually finding the matrix associated to that, even though in my description I didn't even mention a matrix. And the way that I do that is I apply my transformation to each of those standard basis vectors, and then I put those columns in a matrix, and if I put them all in the matrix, that's A, and this is called the standard matrix for the linear transformation. So this is called the standard matrix for the linear transformation T. Okay. All right, so let's do an example of this. So here's an example. So find the standard matrix find the standard matrix A for the dilation transformation T of x is equal to 3x for x in R2. Think about what this does geometrically. So I've already called it the dilation matrix. It takes a vector in R2 and it just triples its length, right? Okay, so how do I do this? Well, going back here, I would take the standard basis vectors E1 and E2, since I'm in R2, I only need two of them, apply the transformation to both of them, and then stick them in a matrix, right? So what is T of E1? So that is the transformation applied to the vector 1, 0. So the transformation takes the vector 1, 0 and multiplies it by 3. So this is 3 times 1, 0, which is the vector 3, 0. Okay, that's easy enough. What about T of E sub 2? So this is the transformation applied to the vector 0, 1. So this is 3 times the vector 0, 1, which is the vector 0, 3. And so A is my standard matrix for the transformation, and it has column T of E sub 1, T of E sub 2. That means it is the matrix reading column-wise now, 3, 0, 0, 3. Oh wow, it didn't matter whether I read column-wise, right? Does E stand for eigenvector? No. We're not going to do eigenvector stuff till chapter 5 in this textbook, so we're a long ways off from eigenvectors. And we'll always use V for eigenvectors anyway. So no, anytime you see E sub I as a vector, that means standard basis vector, E sub I. Okay. All right. So here is my matrix. And so what this means is that another way of writing my transformation T is that this is the matrix A times X. You can just check that. This is 3 times the identity matrix, so it's definitely the same thing. Okay, so that's a really easy way of doing this. Let's do another example real quick. So here's an example. Okay, so let's say let T, which goes from R2 to R2, be the transformation that rotates each point in R2 about the origin counterclockwise by an angle phi. Okay. Now, is this a linear transformation? You could think geometrically for a second and convince yourself that it is in fact a geometric, or it is in fact a linear transformation. Okay. So, how do I do this? Let's look at a picture. So let's, here, I have a straight edge. I can make this nice and straight. So, here's my picture. All right, so let's say, I got a point, this is the point 1, 0. Here's the point 0, 1. And let's say that I have some angle measured here. Let's say we'll call that angle phi. All right, so there's my angle phi. If I'm rotating a point pointed to here, if this point's actually on unit circle, I didn't draw it on unit circle here, but if this point were on unit circle, this would be the point cosine phi, sine phi. That, of course, would get rotated if I'm rotating it counterclockwise by an angle around the origin by angle phi. Then what goes on here? How do I measure in the second quadrant this same angle? Well, measure this in such a way that I have a right angle here, and so the point that this would get shifted to would be minus sine phi cosine phi. Right. Why am I doing this? I'm trying to see how these points are going to get transformed here, right? I want to see how these things get moved from one to the other, right? So what does 1 0 rotate into? So what is T of 1, 0, right? This is T of E sub 1 here. So what is T of 1, 0? Okay, so 1, 0 is going to rotate, since I'm rotating counterclockwise by my angle phi here, it rotates to cosine phi sine phi. So this is cosine phi sine phi, and T of E sub 2 is T applied to 0, 1. What does 0, 1 rotate into? So here's 0, 1. It rotates. This is the same phi here. Right? Now I'm in the second quadrant. I'm using reference angles here and properties of sine and cosine. So what am I doing here? This rotates into minus sine phi cosine phi. So what is my matrix A? So then my standard matrix A is T of E sub 1, T of E sub 2, which is cosine phi, sine phi, minus sine phi, cosine phi. All right. Oh, there we go. All right. Okay. Yeah, so I saw someone was using this with shifted angles. You can definitely do it that way, but I'm just gonna. So you can do it that way with shifted angles, or you can use the fact that if you shift, you can just replace with, you can flip here with a minus sign. So this is my standard matrix. So in particular, this tells me what the standard matrix for rotation about a generic angle is counterclockwise around the origin. So in particular, if I rotate, say, pi over 2, then what is this? A is 0, minus 1, 1, 0. And so you can actually check that if you have a given vector in R2, right, if you multiply that vector by this A, the resulting vector is that vector that has been rotated counterclockwise about the origin by 90 degrees, right, by pi over 2. Okay. All right. Okay. So this tells me that there's a great wealth of examples that I could use here, right? Especially thinking of geometrically what's going on. So rather than draw all those examples out, I'm going to show you some pages in the textbook that are really, really, really nice. So let me, I need to bring this closer to the camera, so I will change the camera here. Okay. So here are a bunch of examples of transformations and what the standard matrix is. I'll have to hold the page down. So reflection through the x sub 1 axis, right? So there's my axes, x sub 1, x sub 2. You see that I have labeled there the vector 1, 0, and 0 minus 1 is labeled here because this takes this image of the fish here and flips it across the x sub 1 axis. So the vector 1, 0 is fixed by that reflection, and the vector 0, 1 gets flipped to 0 minus 1. And you can check that the standard matrix for that reflection is 1, 0, 0 minus 1. Okay, similarly, the reflection through the x sub 2 axis, now it is going to fix the vector 0, 1 and flip the vector 1, 0 to be minus 1, 0. So again, it's the same exact process for finding the standard matrix. 1, 0 gets flipped to minus 1, 0. So in the first column, I have minus 1, 0. 0, 1 stays the same. It's 0, 1. So that column is fixed, just like the first column was fixed in this example. Okay. So reflecting about the line y equals x, or x sub 1 is equal to x sub 2, what happens is these things get flipped to one another. So 1, 0 gets flipped to 0, 1. 0, 1 gets flipped to 1, 0. So since 1, 0 gets flipped to 0, 1, in the first column I have 0, 1. And since 0, 1 gets flipped to 1, 0, in the second column I have 1, 0. Okay, so that is a shift of the columns in the identity matrix. Okay, my reflection through the line y equals minus x, or x sub 2 equals minus x sub 1. So again, here it's flipped, but I have minus signs introduced. So that's what I get in the standard matrix. Similarly, reflection through the origin takes 1, 0 to 0 minus 1, and minus 1, 0, and it takes 0, 1 to 0 minus 1. So this is like minus the identity matrix, right? Okay. So then some other types of transformations, horizontal contraction and expansion. So whether I've contracted this horizontally or expanded it horizontally. So what that would amount to is taking the vector 1, 0, and if I'm contracting, I would be shifting it in. So that is, k is going to be between 0 and 1. And if k is bigger than 1, I'd be shifting it out. I'd be pulling it out this way. In either case, my standard matrix is actually the same because I'm taking the vector 1, 0, changing it to k, 0. 0, 1 is unchanged because this is a horizontal contraction and expansion. So, and 0, 1 is totally unchanged here. So the same exact sort of thing happens when you're vertically contracting or expanding. So here, my fish is getting squished, and here it's getting expanded vertically. So again, here 0, 1 is getting changed to 0k, and 1, 0 is staying the same. So 1, 0 stays the same, and then the second vector goes to 0k. So there's also shears here. So there's horizontal shears and vertical shears done in the exact same way. So you could have a look at those. And then I think there's one more. It's projection, right? So it's completely squishing the image onto an axis. Projection is replacing one of those vectors with the 0 vector. So if you replace the x sub 2 basis vector, so 0, 1 gets replaced with the 0 vector, that's squishing everything to the x sub 1 axis. And similarly, if you replace this basis vector 1, 0 with 0, 0, that's squishing everything onto the x sub 2 axis. Okay. All right. So I'm going to give a couple more examples, a couple more definitions, and then we'll be done for today, since I think I have 1 minute left. So a couple of examples here. So definition: a map. Notice I don't even say linear map, just a map T from Rn to Rm is onto Rm, or surjective is another way of saying this, if each B in Rm is the image of at least one X in Rn. So this is called an onto map, or a surjective map. Okay. And next definition: a map from Rn to Rm is one-to-one, or injective. If you don't like that, you can write it or you can say it like this. So it is one-to-one or injective if each B in Rm is the image of at most one X in Rn. So here it's the image of at least one. Here it's the image of at most one. Those are the two. Those are the two definitions. Now, you might be tempted. We're not 10 minutes over time. We are now 4 minutes over time because I started at 1:07. So you might notice here that the difference might not seem that extreme in this case, but it turns out that these two actually have nothing to do with each other. So you can have maps that are onto and not one-to-one. You can have maps that are not one, or that are one-to-one, not onto. You can have maps that are both onto and one-to-one. You can have maps that are neither onto nor one-to-one. So all possibilities are possible, right? So there's every possible combination of those two properties can be had by a linear transformation. So anyway, this is where I'll pick up on Wednesday. We will finish chapter 1 entirely with our discussion of linear transformations, and that will be that. So remember, you have discussion tomorrow So you have your discussion tomorrow. You'll be going over linear transformations and some of the stuff we've done since last week. Also, I'm having office hours right now, so I'm going to restart the stream so that it's not like one gigantic like 2 hour stream, and I'll be here for like roughly an hour, like 45 minutes to an hour. So you can ask any questions you have about the homework. Your homework is due tonight, remember. So I changed the due date. I extended it by 1 day. So due date is tonight instead. So if you have any questions about the homework or questions about stuff in general, you can come to the office hours. I'm going to send an announcement here in like another minute to Elms, and you guys can show up to office hours. I will list the stream as soon as I end it, so this should be uploaded to YouTube within like a couple hours. Also, yes, like I said, I'm going to send an announcement with the link to office hours because I'm going to reset the stream so that it's not like a 2 hour stream. So anyway, I will see you all in office hours, or if you don't come by office hours, I'll see you all on Wednesday.